Messier 78 is a star formation nursery surrounded by interstellar dust and approximately 1,300 light years from Earth. Euclid's infrared camera revealed previously undiscovered regions of star formation and recorded intricate filaments of gas and dust in remarkable detail. The Euclid mission, directed by ESA, the European Satellite Agency, with cooperation from NASA, has released 5 new photos demonstrating the satellite telescope's capabilities to investigate 2 large-scale cosmic mysteries: dark matter and dark energy. Dark matter is an invisible substance that is 5 times more common in the cosmos than regular matter, but its composition is unknown. Dark energy refers to the unknown source that is causing the universe to expand at an increasing rate. By 2030, Euclid will have created a cosmic map that encompasses almost 1/3 of the sky, employing a much larger field of view than NASA's Hubble and James Webb satellite telescopes, which are meant to examine smaller areas in greater detail. Scientists will then map the existence of dark matter with more precision than ever before. They can also use this map to investigate how dark energy's power has evolved over time. The 5 new photos, which were obtained immediately after Euclid's launch in July 2023 as part of its early release observations program, show views of various sizes, ranging from a star-forming region in the Milky Way galaxy to clusters of hundreds of galaxies. Last year, the mission provided 5 photos from that program as a taste of what Euclid will give, before scientists reviewed the data. The Euclid website hosts the new photos, as well as related scientific articles and data. ESA TV and YouTube have a pre-recorded program regarding these findings. Mission planners for NASA's upcoming Nancy Grace Roman Space Telescope will use Euclid's findings to guide Roman's complementing dark energy research. Scientists will employ Roman, with its increased sensitivity and clarity, to expand the type of science that Euclid allows by analyzing fainter and more distant galaxies. Curved space. Euclid will assist scientists in studying dark matter by examining how this enigmatic phenomena warps the light from distant galaxies, as seen in one of the latest photographs of a cluster of galaxies known as Able 2390. The bulk of the galaxy cluster, which includes dark matter, causes curves in space. Light from faraway galaxies traveling over those curves appears to bend or arc, much like light passing through warped glass in an old window. Strong gravitational lensing occurs when the warping is so powerful that it produces rings, prominent arcs, or numerous pictures of the same galaxy. Scientists studying the impacts of dark energy will focus on a subtler phenomenon known as weak gravitational lensing, which needs intensive computer processing to identify and exposes the presence of even smaller clumps of dark matter. Scientists will explore how the outward acceleration of dark energy has affected the distribution of dark matter by mapping it and tracking how these clusters evolve over time. Because dark energy is a relatively weak effect, we need larger surveys to give us more data and better statistical precision, said Mike Seifert, NASA's Euclid project scientist at the agency's Jet Propulsion Laboratory in Southern California. We can't zoom in on a single galaxy and analyze it in great detail. We need to look at a much larger area while still detecting these small effects. To accomplish this, we needed a specialized space telescope like Euclid. The telescope employs 2 instruments to detect distinct wavelengths of light: the visible light imager, VS, and the near-infrared spectrometer and photometer, NISV. Foreground galaxies emit more light in visible wavelengths, which the human eye can detect, whereas background galaxies are often brighter in infrared wavelengths. Observing a galaxy cluster with both instruments allows us to see galaxies at a wider range of distances than what we could get using either visible or infrared alone, said Jason Rhodes, lead investigator for NASA's Euclid Dark Energy Science team at JPL. And Euclid can make these types of deep, wide, high-resolution images hundreds of times faster than other telescopes. Discoveries beyond dark energy. While the Euclid project focuses on dark matter and dark energy, it also has a number of other astronomical applications. Euclid's Large Area Sky Map, for example, can be used to find dim objects and track changes in cosmic objects, such as a star changing brightness. Euclid's latest scientific findings include the discovery of free-floating planets, planets that do not orbit stars, which are difficult to locate due to their faintness. Furthermore, the data exposes freshly identified brown dwarfs. These objects are thought to form like stars, but are not massive enough to undergo fusion in their cores, highlighting the distinctions between stars and planets. The data, images, and scientific papers coming out now mark the very beginning of Euclid's scientific results, and they show a startlingly wide variety of science beyond the primary objective of the mission, Seifert told the press. What we're already seeing from Euclid's broad perspective has yielded discoveries that investigate individual planets, peculiarities in our own Milky Way galaxy, and the structure of the cosmos on a massive scale. Keeping up with all the advances is both exciting and overwhelming. Hubble photos of the tadpole-like antennae and mice galaxies show the gravitational turbulence they experience. ARP 143, the space triangle, contains a pair of warped, star-forming spiral galaxies. Astronomers believe the duo passed through each other, causing a triangular firestorm of young stars. Mergers like this foreshadow the collision of our Milky Way with the neighboring Andromeda galaxy 4 billion years from today.